In this video, we're going to learn about total and net ionic equations. Before we go into that new concept, though, we're going to focus on reviewing double displacement reactions that involve precipitates or precipitation, which is a precipitate, in other words, the solid chunks that form when you mix two solutions together. We've seen that in the previous unit. So if you don't remember those double displacement reactions, you'll be able to see a little bit of a review if you go back to Unit 2 notes along with the handout. But remember that when we're studying double displacement reactions, we have two compounds, so A, B, and CD, for example. And when they react, they switch cations. The A goes where the C was, and the C goes where the A was. So you have A with D now and C with B. And the idea when we saw this was that you have specific circumstances where reactions can happen. If both products are aqueous, then we say there's no reaction unless, of course, there's a production of a gas by decomposition or water because it's a neutralization reaction. But in general, one of the key indicators that a double displacement reaction happened was if there was a precipitate that formed after our two compounds reacted. And so a precipitate was something insoluble that would form in that solution. So if you need additional information or explanations about the concepts we're going to learn in this video, you can watch the preview the material videos here. And I do recommend that you just try the warm-up calculation before going into the lesson so that you can preview the material from previous class and see how they connect together. Let's go ahead and do a brief overview of double displacement reactions with precipitates. The first thing I'd like you to do before you start the lesson is watch this demonstration and watch a balanced reaction and write a balanced equation for the reaction that you see in the video, and then provide evidence for to illustrate there was a chemical reaction that actually occurred. So watch this video. You'll understand double displacements a bit more if you try out that balanced equation, and you'll also be able to identify what a precipitate looks like when it's formed. And you need that practical experience because eventually you will be doing some hands-on science. So we're talking about precipitation reactions in this case. So double displacement reactions where a precipitate forms. And the reason a precipitate forms is because not all compounds will dissolve in water. When you dissolve compounds in water, in particular ionic compounds, what happens is the water molecules, since they're polar, will be attracted to the charged ions of the ionic compound. And so the partial negative oxygen will surround the cations, the positive ions, and the partial positive hydrogens will surround the anions of the ionic compound, so the negative ion. And if the water is able to separate the ions, then you can dissolve the substance. But not all substances can be pulled apart like that because their attraction, the ions for each other, are just too strong. So let's take a look at the example over here. Here we have two solutions. This is a solution over here of potassium iodide aqueous, meaning that it's dissolved in water and the ions are surrounded by water. And so they're dissolved and you can't see them. And over here we have another solution of lead nitrate, lead-2 nitrate, aqueous. And that aqueous part means that they're dissolved in water. And so the ions are dissolved, surrounded by water, and you can't really see them. There's no solid chunks there. They're not melted, they're dissolved. Keep that in mind. Now, when I pour this solution into this one, you'll notice it's this yellow cloudy substance that forms. Whenever you see a cloudy substance form, that's usually a good indication that you have a precipitate. And eventually, if you let it settle, it'll look like some solid or like some sand sitting at the bottom of water. And that's the precipitate that has formed. So where does that precipitate come from? Well, once you mix these two solutions where everything was soluble, the lead ions and the iodide ions connect together. And they form a new ionic compound. They form lead iodide. And notice they're solid. They're a precipitate. The precipitate is solid. And essentially, water cannot pull these ions apart from each other because they have such a strong attraction for each other. So because they have such a strong attraction for each other, they will not be pulled apart by water, and so they will form a precipitate and will no longer be part of the solution. They won't be dissolved in there. And in fact, you can actually separate the precipitate from this overall solution by basically putting your beaker through some filter paper and collecting the solid that remains behind. And the rest of the solution with the dissolved stuff will go through the filter paper, and you can collect that as well. So essentially, the reason precipitates form is because some substances are insoluble in water, and this happens to be one of them. And so this is a double displacement where a precipitate forms, And when that happens, your double displacement reaction is more specifically called a precipitation reaction because of the formation of a precipitate. So how can we predict if there'll be a precipitate or not? At the grade 11 level, we use the solubility rules, those solubility tables that we saw in Unit 2 earlier. So we're going to spend a little bit of time reviewing some of those solubility rules and solubility charts to predict if substances will be soluble or insoluble in water. So just a few terms to remember or to recall. You would have seen this in the first few lessons of the Unit 4. We have the term soluble and insoluble. So soluble really refers to the fact that something can dissolve in water. And the main definition of that is if more than a gram will dissolve in 100 mils of your solvent, of your water, for example, then we'll consider it soluble. And that depends on things like temperature, for example. So if you look over here, we have NaCl dissolved in water. And when something is dissolved in water, we put AQ next to it, aqueous, because it's dissolved in an aqueous environment, which means water. And so that's soluble. Now, insoluble, if less than 0.1 grams of the solute will dissolve in 100 mils of the solvent, we say it's insoluble. And so you can see here the zinc and the sulfide ions are not separated. They stay together because the attraction between them is so strong. They stick together and water can't separate them. So this is insoluble. And when something is insoluble, we put a little S next to it to say that it remains a solid as opposed to being dissolved like we would put here for aqueous. And so this is the example we saw previously, but now we're going to take a look at how would we know, that this lead iodide is the precipitate in this situation. And so to know that, you'd have to use your solubility rules and charts. And so we had different charts that you were able to use. You can choose to use either one. We'll try this example out to review both charts, and you can take a look at the answer over here as well, just in case you want to see a different perspective of it. The solubility charts are linked here. They're included in your data tables that we've been using throughout the course. So let's look at barium sulfate. We're going to figure out if it's soluble or insoluble in water. So using the general solubility guidelines table here, we compare both ions to each other and see what they want to do. Barium is over here, and notice wants to be insoluble. Sulfate, on the other hand, is over here and wants to be soluble. So they're arguing. Barium wants to be insoluble. Sulfate wants to be soluble. The one that wins is the one that's higher up in the guideline. So for example, 4 is higher up than the 5 in terms of the rank. And so barium is going to win and call the shots. And so when barium combines with sulfate, the compound will be insoluble. And we put a little S next to it to show it's a solid. Another way you could have done it is using this chart over here. Here's barium. Follow the laser pointer until we get to sulfate. There we go. And it says S. And that S means solid. How do we know that? It says that over here. S equals solid, does not dissolve. And AQ would be aqueous, does dissolve. So be sure that you can understand how to determine if a substance is soluble or insoluble, because you'll have to use your knowledge of that in order to write double displacement reactions for precipitation reactions. So you can try these practice problems out here. We'll go try some in the handout when we go fill it out together. But I do recommend you pause the video, try these out, and then you can check your answers afterwards. And then there's some more practice problems here you can try out as well. And a few more here. So the more the merrier. Make sure you get enough practice to make sure you understand how to represent these if they're solid or insoluble. And once you have enough practice figuring out if substances are soluble or insoluble, then you can go back and try to write balanced chemical equations for precipitation reactions. And so I'll walk you through that once we go to the handout. And then we'll also take a look at a bit more of a thinking question that involves these precipitation reactions. Now, before we go to the handout to do those practice problems, I do briefly want to go over where these solubility rules came from. So how do we know, where did this table come from? How did scientists develop it? How is it related to these substances? Why is it that these substances are sometimes solid when they combine with certain ions, or sometimes they're going to be aqueous when they combine with other ions? So it relates to the factors that affect solubility of ionic compounds. There's two main factors that do that. And we can analyze the two main factors over here. So you'll notice that, let's just compare these ionic compounds here. We'll start off by comparing the MgO and the MgF2. First of all, they're both the same. They both have the same cation, so that's not really going to be a factor in affecting their solubility when you're comparing them to each other. But notice that the magnesium oxide has a lower solubility, a smaller number here, than the magnesium fluoride. And so what I want you to see is that the ions here, if you look at the size of the circle, they're very similar in size. But what's different between the anions over here is that this has a larger charge. It's a -2, and this is a -1. So this is a bigger negative charge overall. And so what we say is generally, when the ionic charge increases, the solubility will go down. And that's because if you have bigger charges, like in magnesium oxide, compared to this magnesium fluoride with just magnesium and 1 minus, if you have bigger charges, the attraction between the ions will be stronger, and it'll be harder to separate the ions, and so water won't be able to dissolve it as easily. So when you have bigger charges, then in that case, you're going to have lower solubility. So that's one factor, the size of the charge. The other factor is the ion size itself, the actual radius. So let's go look at magnesium and its compounds that contain the halogens. Notice that they're all a charge of -1. So their amount of charge, or ionic charge, is not going to be a factor in affecting their solubility compared to each other. But notice that they do differ in terms of size, of radius. You'll notice that this is the smallest radius and this is the biggest radius. And you'll probably spot the trend already, but as the size of the ion gets larger, the solubility goes up. And as the size gets smaller, the solubility goes down. And that's essentially because when you have a really big ion, it's hard for the ions to actually connect, to actually hang on to each other, because the nucleus is so far away in the middle. It's almost like trying to hug a big, big tree. You can't wrap your arms all the way around it, so you won't be able to hang on to it very tightly. Whereas if it's a smaller tree, you can hang on to it more tightly. So magnesium can hang on to the smaller radius, because the nucleus is closer, of the fluorine, but not very well to the large radius of the iodine. So when you have a larger ion radius or size, you get a larger solubility because it's harder for the ions to hang on to each other. So all these solubility rules essentially relate to this concept of ion charge and ion size affecting the solubility of ionic compounds. And so now that you know those general rules, you'll be able to solve practice problems like this, for example, predicting which of these would be more soluble. And so we'll do that when we go fill in the handout together. So let's go to our handout right here, and we'll see how much we remember. So as we go through this, remember we were reviewing the double displacement reactions. Our special focus will be on double displacement reactions that produce precipitates. And so the reason precipitates form is because not all compounds are soluble in water or dissolve. And so to figure out if precipitate forms, scientists came up with these solubility rules. Solubility rules or guidelines. And the newly formed solid that will be produced in that double displacement reaction is called a precipitate. Precipitate. And we call the reaction, when you get a precipitate forming, a precipitation reaction. So it's a special type of double displacement that will result in a precipitate or produce a solid. So a precipitation reaction. And a few terms that we reviewed, again, was soluble and insoluble. So soluble, essentially, it dissolves. Insoluble, it does not dissolve. And for soluble, we represent it with the subscript AQ. So when I dissolve salt in water, the salt is aqueous now. It's dissolved in the watery solution. Whereas if something's insoluble, we represent it with the solid subscript. So, for example, zinc sulfide does not dissolve in water, and so we put a little S there. So we saw that to predict if something's going to be soluble or insoluble, you can use solubility rules and solubility tables. And so we had various solubility tables that you could use. And there are a bunch of practice problems you can try to make sure you understand the concept. I'll do a few here with you. I recommend you pause the video and try it yourself first and then check your answers. So for potassium chloride, potassium's here, chloride is over here. Potassium wants to be soluble, it's higher up, so it's going to be soluble. And so if it's soluble, we're going to put KClAQ. Let's look at calcium hydroxide. Calcium's over here, hydroxide's over here. Both of them want to be insoluble, so there's no argument. This is going to be insoluble. And so we can put CaOH2 solid. So going forward, I'm not going to write soluble, insoluble. I'm just going to write the formula with either AQ or S next to it. Again, I'm just using this chart here, but you can use the other chart if you'd like, and you should get the same answers. KOH, K is up here, OH is over here. K wants to be soluble, and it's higher up, so it wins. So this will be aqueous, KOHAQ. PbCl2, that's lead 2 chloride. Lead 2 is over here, wants to be insoluble. Chloride wants to be soluble. Lead 2 wins the game. So we have PbCl2 solid. Let's go and try AgCl. Silver is over here. Whoops. Silver is over here. Wants to be insoluble. Chlorine wants to be soluble, but silver is higher up, so silver wins, and it's going to be insoluble, and we'll have it as solid. Oops, we have it there replicating twice, so let's be successful twice there. Let's see, strontium sulfate. Strontium sulfate. Here's strontium. Here's sulfate. Strontium wins the battle of insoluble. So strontium sulfate is going to be solid. Calcium carbonate. Let's go take a look. Let's go take a look at calcium carbonate. Let's erase this over here so we can have a better view. So calcium's over here. Carbonate is over, where is carbonate? Here. They both want to be insoluble, so calcium carbonate will be insoluble, and we'll have solid. Sodium nitrate. Sodium over here, nitrates over here. They both want to be soluble. Nice and aqueous. Oops, and this one replicates as well. That's okay. We can be successful twice again. So at this point, you know how to use your solubility rules to predict if something's going to be soluble or insoluble. We will do these examples here in another video. To conclude this video, I want to go over the basis of the solubility rules first. Let's go ahead and do that. So here we have the basis of our solubility rules, which comes from two main factors: ionic charge. And we know that as ionic charge increases, the solubility should decrease, because if you have a bigger charge overall, then it's harder for the ions to be separated. And we saw size is another factor. And if you have a larger radius, then the solubility actually increases, because it's harder for the ions to hang on to each other since the nucleus is so far away. And they don't get to kind of combine snugly to each other. So you should be able to answer questions like this after learning about those factors. So try to answer this question, pause the video, and then afterwards play the video and see if you're on the right track. So for this question, you want to figure out which is more soluble, the AgNO3 or the AgCl. So first of all, I want to compare AgCl versus AgNO3. Let's go take a look at what's not considered a factor. Notice that they both have Ag plus 1. So when comparing them to see which one's more soluble than the other, Ag plus 1 is not going to be a factor because they both have that in common. So what's a little bit different though between them? Well, AgCl has Cl minus, and NO3 and AgNO3 has NO3 minus. So notice that they both have the same charge. So we know that charge is not one of the factors. So the only other factor that really remains is the size of the ion. And if you look at it carefully, which ion looks larger? It's most likely the NO3, right? That's a larger ion because you have, 3 atoms that make it up. So this is a larger ion. And so we saw that when you have a larger ion, that will increase solubility. So since NO3 minus 1 is larger than Cl minus, AgNO3 is more soluble. And so you look for the similarities and basically ignore those, or realize that they're not the pardon me, they're not the main factor affecting the difference. So this type, the um, ionic charge, both -1, probably not a factor. The fact that they both have Ag +1, probably not a factor because it's both the same. So what's different is the size of the charge. And so the NO3 is a larger ion, so that means that it's going to be more soluble because they don't combine as snugly with each other. And so our guess was that AgNO3 should be more soluble. And to verify, we can go take a look at our table to see if AgNO3 is soluble versus insoluble for the AgCl. And we can't always verify this way because this table just tells us if something is soluble or not. It doesn't really tell us how soluble it is. It doesn't tell us, this many grams will dissolve in water. So maybe we'll be able to see if we're right. We're not sure. So AgCl, notice AgCl is actually insoluble because Ag wants to be insoluble. But then AgNO3, NO3 is on top here, wants to be soluble. So AgNO3, aqueous, is actually soluble. And so we were lucky that in this case we did have a solid one and a soluble one. And we could check our work. And we picked that AgNO3 would be the more soluble one because of the ion size. So you should be able to explain why certain compounds are more soluble than others using the factors that we described here. In the next video, we're going to try some practice problems for writing balanced equations for the precipitation reactions, and then connect that to the new learning that we're going to do in Unit 4, which is writing net ionic equations.